Hello, my fellow causal champions. I'm Dan Harris, and welcome to Office Hour, where we interrupt our regularly scheduled programs to give me the opportunity to make some clarifications and corrections. So, I want to stipulate at the beginning that if there's something that I'm explaining or trying to say and you're not understanding, it's my fault. Okay, I need to make this stuff as clear as I possibly can, and I made a mistake when explaining the relativity simultaneity experiment, thought experiment that Einstein went through. And that's on me. So I'm going to try to correct that today. I'm going to go over what we should have established up to this point. So up to episode 3, this being relatively up at 3.5. So the first thing that we covered was the Michelson and Morley experiment, which was trying to measure the speed of light as the Earth is traveling fast in one direction, say away from the light source, and really fast in the other direction, moving towards the light source. And it didn't detect a difference in the speed of light. In addition, we covered two theories that tried to explain the results of the Michelson experiment. We covered the special theory of relativity based on the light postulate, which states that light is constant in all directions in all frames, and that's why it appears to be constant regardless of how fast we're moving closer towards the source. Then we had the Lorentz ether theory, which is based on a preferred frame, where this preferred frame is the only frame in which light is constant, and that it only appears constant in all others because all of the frames you have a miscalibration caused by time dilation, length contraction. We're going to get into some of what that actually means and how that addresses this experiment. And in the last episode, we covered the issue with special relativity that leads to an anomaly. So given this light postulate, it led to an anomaly or a contradiction, which is the relativity of simultaneity, where simultaneous distant events is no longer absolute, it depends on your reference frame, which leads to a contradiction. And so I did not explain the experiment setup well in that video, so I'm going to clarify that today for those that were not familiar with the Einstein's thought experiment involving a train and some lightning. So we're going to get into that today as well. I hope you enjoy this office hour with me as we cover these topics on causal discoveries. I suppose the best place to start is the Michelson-Morley experiment and what they were expecting to see. They assumed that there was an ether, which is the background medium which light was supposed to travel through. I don't know if the light ether really exists or not. It's not really important. The important thing was in one inertial frame where this ether was supposed to exist, light is constant, and then all others it's not. And so a frame is just a constant velocity frame of reference. So if you're stationary in space, or if you're moving with some relative velocity and no acceleration in any direction, could be any direction, doesn't matter, it could be this direction, that direction. As long as the velocity is constant, the frame is inertial, and those are the frames that we're discussing, and which one was supposed to be the one that's moving with the ether, so like not the zero velocity relative to the ether. They were trying to detect. And so probably the best place to start is to look at sound, because that's probably the best analogy. It's another kind of a wave that moves through a medium called air. So if you're stationary in the air, then the speed of the sound is same in all directions. If you're moving relative to the air, then your relative speed of sound depends on the direction in which the sound is coming from. So if we were going to conduct this experiment within air, what would happen is you'd have a watch at the start. Sound would the time would start T1, it would bounce off something and then come back and get clocked again at T2. Okay, so you would have this known distance this way, and so the total distance covered would be 2 times this delta distance over T2 minus T1, or delta time, right? So that would be what was expected in terms of measuring the speed of sound. And that's if you're not moving in the air. Now, if you were moving in the air, what ends up happening is, let's say we're moving down. So the device is moving down, the clock's moving down, and so time starts whenever it passes this clock threshold. And say that it would have been here had it not been moving, but since you had some velocity going down, it ends up being down here, right? And so it ends up traveling a little further, and then instead of the clock being here when it comes back, the clock also has some velocity. And so it's, say, at time, so this would be time 1. At time 2, your clock is going to be, say, here. Okay, so the distance covered is different, and the time is going to be different for this experiment. And so you have this distance 1. So we're going to call this delta 1, and then delta distance 1 and delta distance 2. Okay. And so if you could empathize with this device, meaning if you were to go to its reference frame and be stationary relative to it, there is no motion going on here. This is only relative to the medium. And so you have a watch and a mirror, and it's basically stationary relative to its internal reference frame. And what would happen is it would just take longer to make this downward trip. So this downward trip would take some delta t1, and then the return trip would be a lot quicker, delta t2. Okay, and the velocity down, because it's taking longer to make this trip, it's a slower velocity. So relative to the apparatus, it ends up being the speed of sound minus the velocity of the apparatus, and this ends up being the speed of sound plus the velocity of the apparatus, because it's working with the velocity. It's meeting the light on the return trip. And so to look at the average here, it ends up being c minus v, and you're weighting it by the amount of time that is occurring. And then you take the velocity of c plus v, weighting it by the time that it took. And then your average, so then you divide by the weights. And that ends up being your total, or your average velocity. So that's your c average, relative to your, I'll put a 0 here, relative to the reference frame that is the apparatus. Now, it turns out that if you were to simplify all this and solve for everything, it ends up being 1 minus v squared over c squared, where that's your speed through the medium. This is your of sound, speed of sound through the medium, and this is your speed through the medium, and it's all scaled by the speed of sound. So this value is a factor between 0 and 1, and this is your speed of sound. So your average speed relative to the apparatus is a lot slower than the speed of sound, and intuitively speaking, it spends more time going slower than the speed of sound. This takes longer than it's spending going back, so the average ends up being less than the speed of light. So this is a sound example, but they expected this to match with light as well. They expected the light to take longer when you're moving away from the light, and they expected it to take less time when you're moving towards the light. And that's not what they saw. They saw that regardless of how fast the Earth was moving, what direction they were measuring the light, the averaged time it took for the light to go there and back again was always the same, regardless if you were moving or not, relative to where you were. And so this was the puzzling thing. And so the special theory of relativity is based on the idea that, well, the reason you're not detecting a difference when you should is because there is no difference. The light's always moving c no matter what. Whether you're moving relative to where you were or not, it doesn't matter. It's going to take the same time to go down, the same time to go back, regardless of what your velocity is in space relative to any other point. And that's special relativity. And then the Lorentz ether theory is based on that there's one preferred frame. There is a frame in which the velocity is essentially 0 and the speed of light is constant and all others are not. And to explain why you ought to measure a difference in the speed of light but you're not is because of a miscalibration due to time dilation and length contraction. Now, the time dilation is interpreted in this sense as when you're measuring a second, it's actually longer. A second has increased. So your measuring stick for a second has gotten bigger or dilated. And so when you think a second passes, it's actually more than a second because your measuring stick is increased relative to what it would be if you were stationary in this preferred frame. And so that means that it should have taken more time, and it did take more time, but because your measuring stick is bigger, it looks like it took the same amount of time. And then additionally, the distances between here end up contracting. So like for length contraction, what you think is a meter is actually less than a meter because your measuring stick for a meter is contracted. And so while this distance looks like it didn't change, if it got shorter, it would take less time. And so those two together, the fact that your measuring stick for time has gotten bigger and your measuring stick for meters has gotten smaller, compensates for the fact that you're not noticing a difference here. It takes the same amount of return time. And we've seen some of this in the past with other types of clocks. We haven't seen this with length contraction. This is new. But with clocks, it's not uncommon for clocks to become miscalibrated if you move them from where they were calibrated to some other frame where they're not calibrated. So like grandfather clocks, which uses a pendulum to mark an increment of time, the swinging of the pendulum, the period, the time it takes for it to make a complete swing and then back again, takes longer if you move that clock up in elevation. Reason being is the force of gravity is exerting less force on the pendulum, which causes it to take longer to complete its period. And so here's a case where what is being measured as a second with a slower pendulum swing is actually more than a second. So it's not uncommon for timepieces to become miscalibrated. What makes time dilation unique is that it affects every causal event that's transpiring. So anything that takes any amount of time to change, all the duration of that change is taking a lot longer. And so that's the two interpretations of why Michelson-Morley experiment resulted in the way it did. One is the light's always constant, so even if you're moving relative to where you were, it's still going to be constant relative to you in all directions. The speed of light's not changing. Another interpretation, the Lorentz ether theory on the preferred frame, is that it is constant in all directions for the preferred frame, and anytime you move or moving relative to the preferred frame, time measurements are actually being dilated and your length measurements are being contracted, and it compensates for what you would normally expect to see for the speed of light. And that's why your measurements are coming out apparently constant in all frames, is because of the miscalibration. And so hopefully that clarifies the Michelson-Morley experiment, which led to two theories. And then now I'd like to move to why the light postulate leads to a contradiction, but I want to clean up my work here first to get more space. Okay, so for those that were not familiar with the thought experiment that Einstein came up with to determine that simultaneity is relative, I'm really sorry for not going into more details as to the setup of the problem. And so the setup of the problem involves a train car, so that it's just a common location where the events are taking place. Okay, so it's going to be on rails, and in some frames it'll be moving, in some frames it won't. It depends on the reference frame involved. Lightning is going to strike each end. There are going to be two different events, two different lightnings striking each event, and it's going to be instantaneous. The lightning's going to be there in one instant and then gone the next. So lightning's going to end up striking one side of the train, and it's going to strike the other side of the train. It's there and then it's gone. When it's gone, it leaves a trace, a physical trace of that it had existed, which is the light that emits in all directions. But the direction that we're concerned about is the light that's going to reach the middle of the train. So in this thought experiment, the light from each travels through the middle of the car in the form of a wave or wave packet, depending on how you want to say it. But they start off at where the origin of the source is, and then they travel towards the center, and they arrive at the center at the same time. So the time is the same instantaneous point in time, the same place, they arrive at the center. This is the start of the problem. Now we analyze the two facts that have happened so far. Lightning has struck each end, that's one fact. And then the other fact is that the light from the strikes. So lightning struck each end, and light from that lightning emitted in such a manner that it reached the center at the same time from both strikes. Those are the two facts that are common in all reference frames. The disputing facts are which lightning has struck first under this special theory of relativity, where light speed is moving constant in all directions. So in the first case, where you're the observer on the train, let's just say you're standing at the center here, and you're moving with the train, so your relative velocity to the train is 0, and it appears as though you're not moving. According to relativity, that's a very valid frame of reference to consider as stationary. And since you know that lightning struck both ends and it reached the center at the same time, using the light postulate from special relativity, you predict, using that model, that because they traveled the same distance, they're equal. And since the light is traveling at the same speed in all directions, covering the same distance, and they arrived at the same time, you can use the model to back propagate in a forensic type of sense to see where it came from, at what point and when, and notice that it struck at both ends at the same time using this model. And that's, I'm emphasizing using the model. So what physicists have a hard time sometimes distinguishing is model from reality, but not all models are good representations of reality. I don't think relativity is, which is why I'm saying the model is making this prediction. But I'm not saying this is what's happening in reality. There's a difference. This is what we think is happening from this reference frame in reality. When you switch reference frame to a platform such that the train is now moving, I'm going to quickly draw the train in different time frames moving. Okay, and so say you're at the center of where the light comes to as well at this point. Okay, and you're a different observer at this point. You're on a platform. You're seeing this train move with a velocity to the right of some magnitude. Okay, and you see the light strikes the center, and we'll do this backwards in time. So this will be T3 later in time, the time in which you see the light strikes the center, T2 and T1. Okay, so since the light struck the center at the same time, using the light postulate model, you notice that since the train is moving, that the light from the rear had to cover a larger distance than the light from the front did. And why is that? It's because as the lightning strikes the rear of the train, the light from the lightning emits and is, let's say, going through the cabin to the right. The train is moving away from it. So the middle is moving away as the light is propagating. So there's more distance for it to cover by the time it makes it to the center. Now when the lightning strikes the front of the train, the light is, the middle that was here at this point is moving towards the light that's emitted from the lightning, so that by the time the light from the front reaches the middle, it had less distance to cover. And so according to this reference frame, you still have the two pieces of information: light reached the center at the same time and lightning struck at either end, which was the source of this light. And using the light postulate, where the speed of light is moving the same in all directions, because there was a longer distance to cover to the rear, it must have struck first so that it had more time to make up the longer distance than when the front struck, which had less distance to cover. And so this was simultaneous if you're moving with the train according to the model, and now it's not simultaneous if you're on a platform. Now I happen to add a little bit of a flair to it by saying, what if another train were passing this train that had the unfortunate circumstance of being struck by lightning twice? In that case, the exact opposite occurs, where the rear doesn't strike first, it's the front that strikes first, followed by the rear. And just imagine that, this whole thing was mirror flipped. And so basically from this thought experiment, you get the weird anomaly that when, let's start labeling these with letters. When lightning strikes the rear, we'll call that event A. When A occurs, the moment A occurs, there are three things that are true about B, which is B is in the past, B is in future, and B is happening now, depending on your reference frame. And so you can imagine the moment the lightning strikes the rear, you could have 3 different reference frames going through this one point where the lightning strikes. You could have with the velocity equal to 0, you could have a velocity that's negative, you could have a velocity that's positive. And going through this exact same point at the moment that the lightning strikes. And so for this one where the velocity is negative, then that is equivalent to this picture here. And so B is in the future. And then when you're moving this way, that's like the overtaking train. That's the B is in the past. And this is where B is at the same time. So one critical point to this particular example is that each of these frames that exist at A at the same time when the lightning strikes is that their sense of now is the same. It's right now, which means their sense of past, which is before now, is the same, and their sense of future is the same, which is after now. And so that is critical when understanding that B is occurring before, during, and after this A event. And the model, depending on your reference frame, is predicting different things about B at this same exact time. B hasn't occurred yet. It's in the future. B has already occurred and is stopped. The lightning is gone. It was instantaneous and gone. It's in the past. And then there's another one that's like, it's right now. It's happening simultaneously right now. And reality doesn't work that way. The law of identity states things are what they are. So either B exists now, has existed, or will exist, but it can't be all 3 at the same time. And relativity stipulates all 3 at the same time. And that's a blatant contradiction. So that's why the slight postulate is wrong, and why the preferred frame is correct. This whole thing resolves when only one of these is true. Either it's in the past, it's now, or it's in the future for B. And the one that's true is the preferred frame. That's the frame where the speed of light is constant. Well, I hope that clarifies a few things up for you, and if not, just leave a comment or question below and I'd be happy to get to it next time when we do office hours again. And let me know if you like this kind of format. I could do more of it where we peel the curtain back a little bit. I'm not dressing up as anybody and interviewing myself. It's more of a low-key classroom type setting where I'm breaking things down a little bit more so to make sure that my clarity is there. I don't want anyone to be confused, not have a feeling they don't understand, because this stuff is super simple. And if it's not, then it's the fault of the explainer, which is me. So thank you for those that have given me the feedback that led to this video, and I hope you enjoyed it. And until next time, enjoy making causal discoveries.
I ain't gonna give up. Got too little time, I'ma live up. Head down, push forward through the tough times, cause anything worth doing is a tough climb. And I ain't gonna give up. Got too little time, I'ma live up. Head down, push forward through the tough times, cause anything worth doing is a tough climb. Cause I'ma live life for the fight, yeah, I'm here to get it. I got drive, got sight, always have a vision. I go by at night, I be in my feelings, I'ma be